Hello, good afternoon, everyone. I want to continue our math class again this morning. Before that, I will let you, guys, before that, I want you to understand that after this class, I will be dropping some questions in your LMS, 2 questions for your assessment. And I want you to submit it first thing on Monday when we meet at Moivre. The first question is on Venn diagrams, while the second one is on the trigonometrical ratio. So you are going to solve the 2 questions in 2 different sheets of paper. You submit it, I will mark it, and it will be recorded for your assessment. Now let's come to the topic we are looking at this morning, complex number. Now when you cast your mind back, when we are looking at quadratic equation, we talked about the discriminants. And discriminant simply means b squared minus 4ac. And we said that in discriminant, there are 3 cases that we can have. One is when b squared minus 4ac is greater than 0. In that case, you have a real root. But when b squared minus 4ac is equals to 0, you have equal root. When b squared minus 4ac is less than 0, it gives us what we call the imaginary root. And imaginary root is what we call the complex number. Now, as an introduction, the concept of imaginary number has its origin in the fact of the solution of a quadratic equation. Ax squared plus bx plus c equals to 0. That is the general quadratic equation. And if you apply the completing the square method, it will lead us to what we call the quadratic formula. That is minus b plus or minus square root of b squared minus 4ac all over 2a. Now, as I've said, if your discriminant b squared minus 4ac is less than 0, it will lead to what we call imaginary root. So, Euler, one of the great mathematicians, was the one who introduced the symbol for the complex number I, and he said the value is equals to what? Minus 1. Now we have the basic operations in complex number. Let's move to the basic operations. That is, or what we call the properties of a complex number. 1, if you have zi plus zi plus zj, and it gives you zk, we said the property is what? A closure property. When you multiply zi by zj and give you zr, it is also closed. Now when you come to property 5, you see that zi plus zj is equals to zj plus zi. In such case, we said the commutative law is what is applicable. Now we come to rule number 6. Zi times zj equals to zj times zi. That means also that the commutative laws holds. And so on and so forth. We have the distributive law, we have the law of the existence of an additive identity, and also the multiplicative identity. There are about 11 properties as stated in your material. Now we'll move straight at 11 in the first page. We have 12 and 13 in this other page. Now we'll come to this definition that if we have z1 to be equals to x1 plus iy1 and z2 is equals to x2 plus iy2, and both of them are complex number, if we say z1 is equals to z2, what it means is that the real part x1 in z1 is equals to the real part x2 in z2, and the imaginary part in z1, which is y1, is equals to the imaginary part of what? z2, which is y2. Now we look at an example. Let z1 be equals to x plus 4i and z2 equals to 3 plus iy. Now, Z1 equals to Z2 means that X must be equals to 3 and Y must be equals to what? 4. Now we come to the number I. The symbol I was introduced to represent the square root of -1, because when you substitute the value of A, B, and C in that discriminant, when it is less than 0, it will give you a negative number, of which we cannot find the square root of a negative number. And that is why I now is being used to minus square 1. Square root of -1 rather is now used as I in the given equation. So we'll look at some example under it. 1. Simplify the following. I raised to power 8, I raised to power 10, I raised to power 30, I raised to power 19, I raised to power 91. Now for I raised to power 8 is equals to I raised to power 2 further raised to power 4. That is the law of indices, that when you have a base raised to a power is further raised to another power, pick the base and multiply out the power. So if you multiply 2 and 4, it will give you the power as 8. But we know that I raised to power 2 is equals to -1, because square root of -1 is equals to I. So I squared now will give us -1. And -1 raised to power 4, it will give us 1. Again, we have I raised to power 10, which is empty as I raised to power 2 further raised to power 5. And I raised to power 2 is -1. And -1 raised to power 5 is minus what? 1. So that is how we find the value of I in that question. Now we'll come down to the fundamental operations with complex number. In performing operation with complex number, we can proceed as in the way of algebra of a real number, by replacing the I raised to power 2 by -1 where it occurs. The first one, when you have Z1 equals to X1 plus IY1 and Z2 equals to X2 plus IY2, then the addition, the basic operation, Z1 plus Z2, you add the real part, which is X1 and X2, and the imaginary part, which is Y1 and Y2. So Z1 plus Z2 will give us X1 plus X2, the real part, plus Y1 plus Y2, bracket open and close, I outside the bracket. Now the subtraction will also give us the negative of what we have in the first equation. Multiplication, we have X1, X2 minus Y1, Y2 for the real part. For the imaginary part, you have X1, Y2 plus Y1, X2. Now for division, we are going to have Z1 divided by Z2, which is equals to X1 plus IY1 plus X2 plus IY2. Now this one, when you multiply by the conjugate, it will give you X1 plus X2 plus Y1 plus Y2 divided by X2 squared plus Y2 squared plus Y1 X2 minus X1 Y2 divided by X squared 2 plus Y squared 2. Now let's come to practical example. Example 1 says, given that Z1 is equals to 3 plus 4i and Z2 is equals to 2 plus 5i, find Z1 plus Z2, find Z1 minus Z2, that is B. C, find Z1 times Z2, and D, find Z1 divided by Z2. Now let's come to the first one, where we have to find the summation of Z1 and Z2. As I've said, you add the real parts and the imaginary parts. The real part of Z1 will be added to the real part of Z2, and the imaginary part of Z1 will be added to the imaginary part of Z2. Now, if you look at Z1, Z1 is 3, the real part, 4i is the imaginary part. For Z2, 2 is the real part, 5i is the imaginary part. So 3 plus 2 will give us 5, 4i plus 5i will give us 9i. For subtraction, that is B, Z1 minus Z2 will be 3 plus 4I minus 2 minus 5I. If you open the bracket, we are going to have 3 plus 4I minus 2 minus 5I. So if you subtract, you have 3 minus 2, it will give us 1. 4I minus 5I will give us minus I. So Z1 minus Z2 will be equals to 1 minus I. Now, the product of Z1 and Z2, which is Z1 times Z2, it will be equals to 3 plus 4I times 2 plus 5I. That will give us 3 times 2 minus 5 times 5 plus I, 3 times 5 plus 4 times 2. 3 times 2 will give us 6. 4 times 5 will give us 20. So 6 minus 20 will give us minus 14. Now 3 times 5 for the imaginary part. Now 3 times 5 will give us 15. Plus 4 times 2 will give us 8. 15 plus 8 will give us 23. So that is why the product is minus 14 plus 21i. So if you follow the process of division also, you will have 26 over 29 as your real part, minus 3 over 29 as your imaginary what part. Example 2. Example 2. Express each of the following in the form of x plus iy. X is the real part, iy, that is the imaginary part. We have the product of 4x minus 2i and 2 plus 3i. You have minus I plus minus 1 plus I squared, 5 plus I, 3 plus 2I, 2 minus 3I, the product, and D you have 2 minus 3I, 3 plus 2I divided by 4 minus 3I. Now for the first one, 4 minus 2I multiplied by 2 plus 3I, it will give us 4 into 2 plus 3I minus 2I into 2 plus 3I. That will give us 8 plus 12I minus 4I minus 6I squared. So that I squared now will give you minus 1. And if you multiply that minus 1 by 6, it will give you plus 6. So when you add up the terms there, you are going to have 14 plus 8i. Now for the B part of that question, we have minus 1 plus I raised to power 2, which is same thing as minus 1 plus I in another bracket minus 1 plus I. If you open the brackets and simplify, you have minus 2I as your answer. Following the same step, you will have in your question C, 65 minus 13I as your answer. Now the D part of it, which is 2 minus 3I bracket open and close multiplied by 3 plus 2I bracket open and close divided by 4 minus 3I. If you expand the numerator and collect your like terms, you are going to have 12 minus 5I. The denominator is 4 minus 3I. So you multiply the expression by the conjugate. The conjugate of 4 minus 3I is 4 plus 3I. So you multiply the numerator and the denominator by that conjugate. So that will give us 12 minus 5I times 4 plus 3I divided by 4 minus 3I plus 4 plus 3I. So for the numerator, you are going to have 61 plus 16I. For the denominator, you have a whole number 25. So since the denominator is common to both the real part and the imaginary part, you can break the fraction into 2, which will give us 63 over 25, the real part, plus 16 over 25 as the imaginary part. We have some questions, exercises here. Exercise question number 1, 2, 3, 4, and 5. So you can practice all this. Now we come to geometrical representation of a complex number, which is known as the Argand diagram. You can see it there. We have the R, which is the longest side of the right angle triangle, theta as the angle, we have y and x. So z is equal to x plus iy. Now, the definition there is that the absolute value, which is also known as the modulus of a complex number z equals to x plus iy, is defined as the modulus of z equals to the modulus of x plus iy, which is equal to the square root of x squared plus y squared. Now, the properties of the absolute value are listed there from 1 to 10, from 1 to 5. They are all listed there. Now, come to definition 4. Let z be equals to x plus I, y be a complex number. Then the number z cap is equals to x minus iy, and it is called the complex conjugate. The complex conjugate of z equals to x plus iy. Now, the properties of the complex conjugate are listed there. In the material, you have 1, you have 2, you have 3, you have 4, you have 5, you have 6, you have 7, and the last one is 8. You have some exercises again. The exercises are there to help us to walk through what you have learned. And when solving the questions, if there are some difficulties that you experience, feel free to contact me. I will put you through either in a WhatsApp video call or in any means. So come to definition 5. The positive angle between the complex number z equals to x plus iy and the positive real axis is called the amplitude, or what is also known as the argument of a complex number z equals to x plus iy. And this is denoted as Rz, which is equals to theta, and defined by theta, which is equals to arc tan y divided by what? X. Now, the properties of amplitude are listed there in the material. Now, look at the first example. Given that z is equals to 3 plus 5i, and z2 is equals to minus 5 plus 4i, and z3 is equals to minus 2 minus 3i, and z4 is equals to 7 minus 5i. We are asked to represent the complex number on the Argand diagram and find the modulus and the argument of z1, z2, z3, and z4. Now you can see the diagram in the material here. This one is the representation of the complex number of the equation z2 equals to minus 5i plus 4i. This is for z1 equals to 3 plus 5i. This one is for z3, which is minus 2 minus 3i, and the last one, which is z4, is minus 7 minus 5i. That is the representation. Now we'll come to question number B. To say find the modulus and the argument of z1, z2, z3, and z4. Now for z1 equals to 3 plus 5i, the argument is just taking the square root of the square of both the real and the imaginary part. The real part here is 3, the square of it is 3 squared. The imaginary part is 5, the square of it is 5. So the square root of 3 squared plus 5 squared will be equals to 3 squared will give us 9, 5 squared will give us 25. 25 plus 9 will be 34, which gives us the square root of 34. That is for B1. So you follow the same procedure in others, you arrive at the answer. Now for the angles, which is equals to tan 4 all over minus 5, tan y all over x. So it will give us minus 38.65. We have done quadrants. In first quadrant, all trig ratios are positive. In second quadrant, sine is positive. In third quadrant, tan is positive. In the fourth quadrant, cosine is positive. And for us to convert angle in the that is negative, tan, we know that tan is positive in the third quadrant. So how do we convert an angle in third quadrant to an acute and convert it is by adding 180 degrees to it. It will give us a positive angle 141.34 degrees. So you follow the same procedure, you will have 236.31 for Z3, and for Z4, you have 324.46 as your what? As your answer. Again, you have an exercises under it, practice it, and let me know. I think when we meet at home here, we'll be able to go through all these exercises, and I will also explain more on all these topics that we have done. Now we'll look at polar representation of a complex number. The complex number z equals to x plus iy can be expressed in terms of its modulus and argument by the relation z equals to r bracket open cos theta plus I sin theta as follow. One, you see the diagram given below. We know that cos theta, right angle triangle, cos theta is equals to x all over r, where x is the adjacent and r is the hypotenuse. So making x the subject of formula there, x will be equals to r cos theta. Sin theta is equals to opposite all over hypotenuse, and making the side opposite the subject of formula y, it will give you r sin theta. So z equals to x plus I sin y will give us r cos theta plus I r sin theta. And as you can see, r is common. You factorize that to r, it will give you r into cos theta plus I sin theta. So z is equals to r bracket open cos theta plus I sin theta is called the polar representation of a complex number. Now let's look at example 1. Z1 is equals to 2 plus 3i and Z2 is equals to minus 3 plus 4i. Obtain the polar representation of Z1 and Z2. So Z1 is equals to 2 plus 3i. So for us to find the modulus, we have square root of 2 square plus 3 square, which will give us square root of 13. And for us to find the angle, it is the arctan of y all over x, which is going to be 3 all over 2, and that is equals to 56.31. So Z1 will be equals to square root of 13 cos 56.31 plus I sin 56.31. So that is how we calculate that. So that we also have an exercise under it. We practice this question again. Now we have theorem. If Z1 is equals to R1 cos theta 1 plus I sin theta 1, and Z2 is equals to R2 plus a bracket open cos theta 2 plus I sin theta 2, then the product, that is the multiplication of Z1 and Z2, will give us R1, R2 cos bracket open theta 1 plus theta 2 plus I sin theta 1 plus theta 2. 2, Z1 divided by Z2 will give us R1 divided by R2 cos bracket open theta 1 minus theta 2 plus I sin theta 1 minus theta 2. We have the proof there. For your own consumption, you can go through it, but it's not necessary as far as this course is concerned. So no one will ask you to derive this formula. Now we always ask you to apply it. Now, given that, for example 1, Z1 is equals to 2 root 3 minus 2i, and Z2 is equals to minus 1 root 3i, obtain the polar representation of Z1 and Z2 and find Z1 times Z2 and Z1 divided by Z2 in polar form. Z1 is equals to 2 root 3 minus 2i. So Z1 will be equals to 4 into cos 11 over 6 plus I sin 11 over 6. And Z2 is equals to 2 into cos 2 power over 3 plus I sin 2 power over 3. So Z1 times Z2 will give us what we have there. And if you simplify, you are going to have 8 bracket open cos 5 power over 2 plus I sin 5 power over 2. For the other one, Z1 divided by Z2, you have 4 into 2 bracket open cos 11 power over 6 minus 2 power over 3 plus I sine 11 pi all over 6 minus 2 pi all over 3. So when you subtract 11 over 6 minus 2 pi over 6, it will give us 7 pi all over 6, which will now make our answer to be equal to 2 cos 7 pi over 6 plus I sine 7 pi all over 6. So that gives us the answer to that question. Now look at the De Moivre theorem. In the Moivre theorem, we said that let z be equals to r cos theta plus I sin theta, and it is a non-zero complex number. Then z raised to power n is equals to r raised to power n cos n theta plus I sin n theta. That is the De Moivre's theorem. And you can use De Moivre's theorem to solve some example, like what you have there. Given that z is equals to 1 plus I, find z raised to power 20. In this case, z is equals to 1 plus I, which is equals to square root of 2 cos pi all over 4 plus I sine pi all over 4. Z20 will be equals to 2 raised to power 1 over 2 further raised to power 20 cos 20 pi all over 4 plus I sine 20 all over pi all over 4. So 2 raised to power half raised to further raised to power 20 will give us 2 raised to power 10. 20 divided by 4 will give us 5. That is why I have cos 5 pi minus sine 5 pi. So that in summary, you have 2 raised to power 10 cos 5 pi plus I sine 5 what? Pi. Now we have example 2, given that z is equal to minus 1 over 2 minus root 3 all over 2I, find z20. So you do it yourself. Now simplify cos 3 theta plus I, 3 theta over cos theta I sine theta. So in this case, we have cos 3 theta plus I sine 3 theta over cos theta plus I sine theta. You multiply by the conjugate of the denominator. The conjugate of the denominator is cos pi plus I sine cos theta plus I sine theta. So the conjugate is now going is cos theta plus I sine theta. So you multiply both the numerator and the denominator by the conjugate. So we have cos 3 theta plus I sine 3 theta divided by cos theta plus I sine theta times cos theta minus I sine theta, that is the conjugate, all over cos theta minus I sine theta. So if you simplify it, we're going to have cos 2 theta plus I sine 2 theta. We are asked to use the Moivre theorem to show that cos 3 theta plus I sine 3 theta divided by cos 5 theta minus I sine 5 theta will be equal to cos 8 theta plus I sine 8 theta. So you have the solution there in your material. Now we'll move straight to we'll move down to the nth root of unity. It is a special case in which z is equal to 1. Z is equal to 1. So the special case in which z is equal to 1 is of particular interest that lead to the n distinct roots of 1, and they are called the nth root of unity, and is given as z is equal to cos theta cos 0 degree plus I sine 0 degree. Now, this will be equal to WK, which is equal to cos 2k theta pi all over n plus I sine 2k pi all over what? N. So that is what we call the nth root of what? Unity. Now we come to the Euler's formula. In Euler's formula, from our idea of infinite series, we know that exponential s is equal to 1 plus x squared divided by 2 factorial plus s cubed divided by 3 factorial, and so on and so forth. You also have another infinite series of cosine cos x and that of sine x. So all these one holds when we substitute s is equal to minus I theta in equation 1, and using 2 and 3, we'll arrive at the result e raised to power I raised to power e raised to power I theta is equals to cos theta plus I sin theta. This equation 4 is what we call the Euler's word formula. And when you multiply the equation 4 by r, we're going to have r e raised to power I theta equals to r cos theta plus I sin theta. And from here, we know that r cos theta plus I sin theta is equals to z. So z is equals to r e raised to power I theta. So Zn will now be equals to r e raised to power I theta plus e raised to power n. So which give us r raised to power n, e raised to power I, and that is in of what? N of theta. I take that again. Zn is equals to r exponential I theta raised to power n. And when you expand that, you are going to have r raised to power n exponential I n theta. So in exponential form of a complex number, theta is usually measured in what? In radian. And we have looked at how to convert from radian to degree and vice versa. So we also apply it at this point. Example 1 says, given that z is equals to 1 plus 2i, find z raised to power 6 in exponential form. We have z equals to 1 plus 2i. The modulus is going to give us square root of what? 5. And the angle is going to give us 63 degrees. And when converted to radian, is equals to 7 pi all over 20. So when you substitute in the Euler's formula, you're going to have 5 raised to power 3 exponential I theta all over what? 10. So you follow that same procedure, you solve this example 2, and you arrive at the what? The answer. So we'll be calling it a day here, but I also want you to look at these miscellaneous questions. When we meet at Umonia, we'll look at polynomial and binomial theorem before we now go to our revision. So we'll stop here so that you'll be able to have time to go through all that we have discussed. But don't forget that 2 questions, 2 assignments will be uploaded in your LMS. You are expected to solve them, and it is the first thing you will submit on Monday when we meet at Omenia. Thank you, and bye-bye at this point.